This is session 3 for Models in Epidemiology and Biostatistics. My name is Gordon Hilton Fick, and today we, I guess you could say, finally begin talking about models. And we're going to build on material that we've established in sessions 1 and 2. Indeed, we're going to take an example that we saw early and make it a logistic regression. We're going to see that much of what we've done so far can be duplicated by a model, by logistic regression, as we'll see. And that from this logistic regression, we'll actually get more. And more on that as we move forward. So let's just review a couple of key things. The logit is a name for the logarithm of the odds. So we can notice that the odds, and remember that the odds can be any positive number. A reminder again that odds are not probabilities. Probabilities are between 0 and 1, but odds can be greater than 1. The log of odds then can be any number. We will see that as we begin to interpret things that involve odds and log of odds, we're going to want to keep three things about logarithms in mind. If the odds is 1, the log of odds is 0. If the odds is less than 1, the log of odds is less than 0. And if the odds is greater than 1, then the log of the odds is greater than 0. Basic facts that come from logarithms. And I thought what I would do is establish some of the key pieces as though the study that we are analyzing is a case control study. Everything here can be repeated for cohort studies or any prospective study by interchanging exposure and disease. But as you'll see later on in this session, there are important issues concerning odds ratios in the analysis of case control studies and also in other studies for which odds ratios are often used. So we have the same labeling as before, exposure and disease, and we can have the strata. What we've seen so far in sessions 1 and 2 are examples where there's no strata, the so-called crude situation. There's where there's one strata with two members or two levels. Right? We can have a strata that has 4 levels, as we've seen, that was based on 2 explanatory variables. But in fact, we can have strata that have 3 levels, 5 levels. The number is not specified here. And as before, we'll use the same symbolism for the young and the old and the male and the female. Only now we're going to be, in the case of a case control study, we're now going to be dealing with probabilities and odds that are in terms of exposure. In other words, we're going to be reversing things. We're going to be discussing the probability of exposure given disease and the probability of exposure given the absence of disease. Keep in mind with a case control study that it is exposure that is the outcome, and that the case control status is something that's specified by the investigator. It is an explanatory variable then. So we have the odds of exposure for those who are cases and the odds of exposure for those that are controls. Just like before, although the notation we're using has been switched. I hope that's fairly clear. So we come now to our first model, and we'll call it model number 1 for this illustration, this session. So a logit, or a log of odds in an equation. Now we're going to have the quantity P, which we've seen can be P0 or P1, a conditional probability of exposure, then the probability divided by 1 minus the probability is the conditional odds of exposure. Here we're saying conditional on disease status. Okay, so let's write an equation, the simplest possible, almost the simplest possible, but for our purposes here, the simplest. That is that the log of the odds is beta naught plus beta 1d. You'll recall that d is either 0 or 1. It is 0 for those who are controls, and it is 1 for those who are cases. So we can see right away that this very simple equation specializes to the two cases. We can see that the log of the odds of exposure for those who do not have disease is beta naught. Notice that is the log of the odds of exposure for those who do not have disease. Okay? And then we see that if we set d equals 1, we get that the log of the odds of exposure for those with disease is beta naught plus beta 1. In the modeling literature, these regression coefficients, beta naught and beta 1, are essentially the key pieces to this model. We wish to understand what beta naught and beta 1 are. Well, right off the bat, we can see what beta naught is. Beta naught is the log of the odds of exposure for those who are controls. And beta naught plus beta 1 is the log of the odds of exposure for those who are cases. That just is immediate. There's nothing fancy happening here at all. Notice that d can only be a 0 or a 1. There's nothing else here but d equals 0 or d equals 1. The two cases. The consideration of d equals 0 for controls and d equals 1 for cases. So what do we get? That beta 1 is in fact a difference between two log odds. Just subtracting the second equation from the first, specialized, gives us that beta 1 is the difference between two log odds. It is indeed the log of the odds of exposure for those with disease minus the log of the odds of exposure for those without disease. Okay, so we have now provided an interpretation for beta naught and beta 1. How does the odds ratio come into play here? Aha! Let's take the exponent of beta 1. You'll recall that the exponent is the inverse of the logarithm. We can then say that the exponent of beta 1 is indeed the ratio of odds. Just have a look at that. It's a little bit elaborate. What have we done? We've taken the difference between two logarithms and written it as a logarithm of a ratio. And then we've taken the exponent. And there's our odds ratio. That means that the exponent of beta 1 is our odds ratio. How about that, eh? It's the odds of exposure for those with disease divided by the odds of exposure for those without disease. Yeah. All right, well, let's make things a little more elaborate then. Let's suppose we wish to add to consideration now whether or not the participant in the study was a smoker. So we'll have two values. We'll have the odds ratio for the smokers when the strata is coded 1, and the odds ratio for the non-smokers when strata is coded 0. And what do we get? Well, we get the population version of two 2x2 tables. We get the 2x2 table for the smokers with s equals 1, and the 2x2 table for the non-smokers with S equals 0. Here you can see I'm using the codes for things here, illustrating things. That means that we have an odds ratio for the non-smokers and an odds ratio for the smokers. And they're written there, OR0 and OR1. We get two odds ratios. Now, this is, I hope, taking you back to what we did in the very first session. Two odds ratios, right. Okay, now let's start with what looks like a pretty intimidating looking expression. This equation that has now 4 regression coefficients. Beta naught, beta 1, beta 2, and beta 3. Further, we've got beta 1 multiplied by d again, but now we're going to have beta 2 multiplied by the indicator for smoking status, and then lastly this complicated looking thing, which is the product of 3 things. It's the product of beta 3 and disease indicator and smoking indicator. That looks rather daunting. On the other hand, remember that D can only be 0 or 1, and S can only be 0 or 1. That means there's only 4 circumstances here. You might be thinking, that's way too much. But it isn't. Have a look now if we specialize that equation to the case when we have controls that are non-smokers. That means that D is 0 and S is 0. And the only expression or regression coefficient that survives is beta naught. In other words, beta naught now is the log of the odds of exposure for the non-smoking controls. Aha! Now we can do the same thing for the non-smoking cases. The smoking controls and then the smoking cases. Now you can see we now get all the possibilities. We write that equation in a somewhat sophisticated way as one line, but it in fact specializes to exactly 4 circumstances. And there they are. We've got the only possible circumstances. Now, what are we going to do with that, though? How are we going to make sense of those 4 things? Those 4 equations again. Well, we take differences again. If you take the difference between the log of the odds of exposure for the non-smoking cases, and subtract the log of the odds of exposure for the non-smoking controls, we get beta 1. Again, by taking the fact that that difference, the difference between the 2 logarithms is the logarithm of the ratio, we see that the log of that particular ratio is beta 1. What is that? Well, that's the log of the odds ratio for the non-smokers. Right? We've got disease status on the top and control status on the bottom. And it's specific to the non-smokers. And for the smokers, what do we get? We get something almost as simple. We take the difference between the log of the odds of exposure for the exposed smokers and subtract the log of the odds of exposure for the unexposed smokers. When we do that, we get again a difference between 2 logarithms. And then we can see we get the logarithm of a ratio. Aha! So beta 1 plus beta 3 here turns out to be the log of the odds ratio for the smokers. Huh. Going back to our labeling that we did earlier, we see that beta 1 is the log of OR sub 0. And beta 1 plus beta 3 is the log of OR sub 1. Just going back to this display. There's the odds ratio for the smokers. There's the odds ratio for the non-smokers. Okay. Right. So now we can interpret beta 1. That's pretty straightforward. You just got that. Aha. What about the setup here again? Let's revisit this from a slightly different point of view and specialize the equation in a slightly different way. Let's just specialize the equation for just the non-smokers and just the smokers. And we get those two equations, both involving disease status. But now we can directly see that for the non-smokers, that beta 1 is the log of the odds ratio, just as we saw in the previous slide. And similarly, that beta 1 plus beta 3 is the log of the odds ratio for the smokers. Again, we can specialize the algebra here a little bit, and I would encourage you to spend some time confirming that you understand what we're seeing here. Again, I have done this now in two different ways. It's a little bit intimidating at first, but frankly, not that bad. Okay. Now we've got something new. Okay. What have we got? We've got the odds ratio for strata 0, that is the non-smokers. That's the exponent of beta 1. And we've got the odds ratio for strata 1, which is the exponent of beta 1 plus beta 3. Huh. What is the exponent of beta 3 then? Huh. Just the ratio of those two odds ratios. Oh, it's a little bit technical here, a bit confusing maybe. Hope not. But if you take the ratio of OR1 to OR0, the only thing that survives is the exponent of beta 3. On the other hand, we can now see that beta 3 is the difference between two log odds ratios. Wow. The difference between two log odds ratios. Notice we are taking differences again and then taking ratios. So I'm showing you this in two different ways. And again, although you may be thinking, man, there's a lot of math here. On the other hand, it turns out to be so important. Do spend time familiarizing yourself with these issues. Big payoffs here. It isn't that intimidating, and I hope that you'll agree that understanding how to interpret these pieces will take you a long way to understanding and demystifying what are logistic regressions. So, let's go back and assess modification like we did in the previous classes. What do we know about this particular situation if beta 3 is 0? Beta 3 is 0. That says that the two odds ratios are the same. That the odds ratio for the non-smokers is equal to the odds ratio for the smokers. Go back and look at the equation again if you're not quite sure. That says that if beta 3 is 0, then smoking is not a modifier because the two odds ratios are the same. On the other hand, if beta 3 is not 0, then the two odds ratios are not the same and smoking is a modifier. Aha. If smoking is a modifier, well, that means we need to present the stratum-specific odds ratios because they're different. Both odds ratios need to be interpreted with separate estimates, and in principle, separate confidence intervals and tests of significance. Notice here it would be misleading to report a single odds ratio. If odds ratio for the smokers is different from the odds ratio for the non-smokers, then attempting to combine the two means we would have an odds ratio that refers to nobody. It doesn't refer to the smokers, and it doesn't refer to the non-smokers. I am always influenced by one of my mentors, Professor Daniel Delury, and one of his best quotes, in my opinion, was, "As a matter of statistical decency, we never average things that differ through more than error. To do so is to distort and deceive." Professor Delury's quote about statistical decency. Yeah. And any attempt at finding a single odds ratio is inevitably a combination of two different odds ratios. And we can say, if we try to do that, are we distorting or deceiving? Yes, indeed. On the other hand, if smoking is not a modifier, then we could say, all right, we now have two odds ratios that are the same. In other words, we have an assumed common odds ratio. We might still be able to report the crude as well. We have to figure that out. And we're going to see now that the model-based process here is essentially the same as the stratified analysis. However, we now need to take on another model. And we'll call this one Model 3. So just to keep you up to date here, we've got Model 1, which was the crude. Model 2 was the one that included 4 terms. And now Model 3 is the model that does not include the 4th term. In other words, there is no beta 3. Another way of observing this is that if we're prepared to assume that beta 3 is 0, that means we need to reconsider the equation. Equation based on Model 2 with beta 3 equals 0 gives us this equation now, where we have the log of the odds of exposure being now the sum of only 3 terms. Again, what we're going to do, as we did earlier in this session, we're going to specialize this equation to the 2 cases, to the smokers and the non-smokers. When S is 0, we get this equation. When S is 1, we get this equation. What do we see now? If S is 0, we're speaking about the non-smokers. And we see that beta 1 is the log of the odds ratio, and that's the same as before in Model 2. But now notice that if S is 1, if we're speaking about the smokers now, then again beta 1 is the log of the odds ratio. The odds ratio, then the log of the odds ratio, applies to both the smokers and the non-smokers here. The same coefficient applies to both. And then we can check that. Here's the checking process. A little bit of algebra again. In other words, we get that beta 1 is something very familiar to us that we saw in stratified analysis. Beta 1 is now the log of the odds ratio for the smokers, and it's also the log of the odds ratio for the smokers. Did I say that right? The non-smokers and then the smokers. In other words, the exponent of beta 1 is the assumed common odds ratio. Wow. Now we see that Model 2 can be compared with Model 1. In other words, we can now compare, I guess I call that Model 3. Model 3, the one we've just looked at, and Model 1. And we can compare the adjusted odds ratio from Model 3 with the crude odds ratio from Model 1, just like we did in the stratified analysis. Oh boy. Yeah. Now, it's something that will pop up over and over again and is crucial to understanding models in epidemiology and biostatistics, is as soon as you change a model by either adding a term or deleting a term, all of the regression coefficients change in their interpretation. This is unfortunately mishandled in lots of places, so I'll be emphasizing this a lot. We need to reinterpret the model equations each time we remove or add a term or terms. It's time-consuming sometimes. So I've tried a model with one set of terms, and now I'm trying a model with, say, another term added or another term removed, and everything needs to be reassessed. The meaning of the coefficients must be reconsidered every time we change the model. It is simply a fact. Don't attempt to oversimplify it and think, oh, I know what that number there is, that regression coefficient. It's the same all the time, and that's never true. It is never true, full stop. Another piece of terminology that I think is worth commenting on. In the second model, we had the 4 terms on the right-hand side of the regression equation. And the fourth term involved a product of 2 indicator variables here: disease status and smoking status. That product enabled us to provide an important interpretation for beta 3, something that really helped us throughout this process. In this particular instance, that model with those 4 terms enables us to interpret the regression coefficient beta 3 as the thing we want to use to assess modification, the presence or absence of modification. And we can see that as we will become fairly clear as you become accustomed to these things, but we need all 4 of those terms present most of the time. There are highly specialized circumstances when 1 or more terms in a model may be excluded, but we'll leave that for now. Now, that product of those 3 things, the regression coefficient beta 3 times D times S, is sometimes called an interaction term. Many of you may have seen the word interaction in previous courses you've taken or in previous reading. Now, interaction, it turns out, has several uses, as we will see moving forward. It turns out that interaction in Model 2 enabled us to assess modification. But we'll see that the use of these so-called interaction terms actually also enables us to assess elaborate forms of confounding. And it also enables us to assess models in which there's more than one exposure or more than one disease status. So I think it's probably wise when you are using this terminology to think of interaction as a rather generic term. Keep confounding and modification as specific to the epidemiology at hand. And the use of the term interaction, we will see, applies to a wide range of circumstances and not just the one we've just illustrated. So I do not recommend thinking of interaction as a synonym for modification. Modification has very specific definitions, and interaction has its own set. There's some overlap, but that doesn't mean they're the same. Okay. And now I've just mentioned here that if with every model you construct, you need to interpret the coefficients. As soon as you exclude or remove a term, you get different things. As soon as you add a term to a model, you get different interpretations. I strongly recommend that you take a couple of minutes and go back to the slides where we're introducing Model 2 and provide interpretations for beta naught, beta 1, and beta 3. We've already done beta 3. But try and do it for all of them. All of them have valid interpretations. It's worth spending some time with this now. You can do the same thing with Model 2. Okay. Now, who's this guy? Well, this is arguably statistics' most famous contributor, Ronald Aylmer Fisher. And he is responsible for an overwhelming set of things that are used in epidemiology and biostatistics. In fact, epidemiologists often claim him as a major developer in epidemiology, and that's true. But he's also a major developer in statistics. And we'll leave out the other things, but he was involved in other fields as well. A remarkable man in so many ways. Professor Fisher wrote the initial paper on something called the likelihood function way back in 1922, yeah. And it is still being mined by researchers looking for ways to expand and use the likelihood function. It turns out the likelihood is behind the logistic regression that I've just introduced you to. It's certainly much more mathematical. That's not our goal here. There's going to be a little bit more math as we move forward, but I don't think it's going to be too bad. For sure, in my humble opinion, the two finest resources for this material continue to be Jim Caldflesh's book, published in 1985, Volume 2, and that's where I cited that illustration that was used in Session 1. Probably still today, the finest book written on the mathematics behind probability and statistics, in my opinion, is the book by Don Fraser, D.A.S. Fraser. He wrote the book in 1976. Yours very truly was involved with a number of aspects of this book when I was a graduate student. And indeed, I co-wrote the solutions manual for that book and contributed a number of other pieces to it. I was quite involved in that book, and I still highly recommend it. So the likelihood function has a very simple definition. It's a function that's proportional to the probability of the observed. That doesn't sound like much, but that's what it is. So, how does likelihood enable the estimation of the unknowns? Well, for every model, once we get our data, we're going to have what's called the observed likelihood function. And it's a function expressed in terms of in our case, the betas. Beta 0 to beta whatever, beta k. And it is argued in many places that one should find the maximum of this function. That maximum height, if you like, for this function, then gives us estimates of the unknown regression coefficients. In this particular case, they're called the maximum likelihood estimates. Very widely seen. And it turns out that that function is used to that likelihood function, the observed likelihood function, is used to compute other things. It is essentially the basis behind the determination of standard errors for the estimates and confidence intervals for the regression coefficients. These are based on some fairly elaborate stuff, so-called approximations based on parabolas that basically give us something that's close to the actual likelihood curve. A little bit more of the math then here. Let's take a quick look. You may want to skip this for the first read-through, perhaps. Maybe a tiny bit more math here. This is one of those occasions in which we're going to be at least referring to a little bit of calculus from. But again, this is not particularly advanced, but in any case, here's what we get. We're dealing with the actual likelihood function and an approximation to it that is used to determine the characteristics. Once we've determined the maximum likelihood estimator, we can then take the likelihood function, for example, a situation in which we have the study of just the prevalence, say the prevalence of some disease, and without any other explanatory variables, this likelihood function has only one unknown parameter, and that is p. It turns out that this function is very closely approximated by a parabola that looks like this. How that's done? Well, a little bit of math, and you may want to refer to one of the books I mentioned just earlier. The more crucial thing is the log likelihood will be approximately equal to this quantity m minus something that's positive. Okay, that makes sense, doesn't it? Then m is the maximum, because no matter what this thing is, that we can see that it's a positive number that's being subtracted from m. A little bit elaborate. So here's the log of the odds, the maximum likelihood estimate, and the standard error for it. Ooh, all of the things that we want when we're trying to understand likelihood functions. Well, here's just very briefly how we can coax Stata into doing some analysis for us here. This simple data set in which we have an interest in studying the prevalence of disease. And for the sample, we'll suppose that there are 3 in a sample of 5 that have disease. Okay. I can then use this very simple logistic regression equation, which we'll be seeing quite a bit later on in this session, to construct an estimate of the maximum likelihood. This is the maximum likelihood estimator. There's the standard error for it. And then we have a z statistic and a confidence interval and a p-value. All the key ingredients in basic statistics: estimate, standard error, ratio of estimate to standard error, p-value, confidence interval. All based on the approximating parabola. This number, 0.405, is an estimate of the logarithm of the prevalence here. It is the MLE. So we can see that the equation that we have, substituting in the maximum likelihood estimate and the standard error of the maximum likelihood estimate, gives us the approximating log likelihood function for this data set. And then you can see we get some numbers. All of this can be worked out. Here's a visual, though, of the two. The actual likelihood function in this simple illustration is this blue curve. The approximating parabola is the red curve. Does a pretty good job, at least when you're close to the maximum here. You can see the approximating parabola is close. And this is for a very small data set too, only n equals 5. Okay, that's enough of the really heavy-hitting stuff, the heavy-hitting math. Let's now summarize where we are and where we're going to be going. The theory that we're using, that's implicit in all of the models we're going to be looking at for the next while, involve a model which will be the log of the odds being equal to a linear combination of regression coefficients times explanatory variables. This is the model with the unknown probability or odds in here, and the regression coefficients. These are the unknown characteristics. We then will construct a fit that will look like this. We'll have the fitted probabilities here that can be computed when we substitute the unknown regression coefficients for their estimates, where the estimates are the maximum likelihood estimates. This rather, again, somewhat intimidating looking expression can be written in terms of the estimate or the fitted probabilities directly with just a tiny bit of math. Now notice here I'm using a hat over the regression coefficients or the Latin equivalents. And in the literature you'll see both. Perhaps it's just a little less cluttered to use the Latin letters. But both are seen, and I will use both somewhat interchangeably here. So the beta with a hat over it is the estimate, and the B is also the symbol for this thing. Okay. Okay, what have we got now? We're going to have a model. Then we're going to find the maximum likelihood estimate. And Stata does this for us. Or R or any software tool will give us these characteristics. It turns out that this fit can be used with any set of explanatory variables, or any values for these explanatory variables, to get an estimate of conditional log odds. And then we can solve that to get conditional probability estimates as well. Notice now that we have two things. We've got the coefficients. Those are the unknown population characteristics, the betas. When we construct a fit, we then will have estimates of those regression coefficients. So it means that once we've constructed an interpretation for a regression coefficient, then once we get its estimate from a fitting procedure, then all we have to do to the description is add the phrase an estimate of. So, for example, if we have in our very first model, Model 1, the so-called crude model, we see that beta 1 is the log of the odds ratio. Right? The log of the crude odds ratio, if you wish. Then B1 is then an estimate. It is the maximum likelihood estimate of the log of the odds ratio. My. It all starts to come into play. I hope you're seeing that. Now, some more details, and again, there's quite a bit going on here, but I hope you're with me. And you may wish to review the slides, review this video. We're getting estimates and confidence intervals, as we'll see throughout this course, from methods based on maximum likelihood. We can see that, and we will see, that the odds ratio estimates we get in models 1 and 2 are the familiar estimates we get from the stratified analysis. Turns out they are, in fact, exactly the same. So the methods used for estimation in stratified analysis for models 1 and 2 are in fact the maximum likelihood estimates. Model 3, the one that did not include beta 3, when we were assuming beta 3 was 0, it turns out there's a little more at play here. Model 3 does not give us exactly the same odds ratio estimate as the Mantel-Hansel estimate we get from stratified analysis. Now, this is a bit of an issue, and if in fact one considers both, maybe you tried a stratified analysis and then tried Model 3 and saw that you got different numbers, then there are issues in play that need to be considered. And in fact, the crucial issue in fact with Model 3 as our first illustration is that the approximation methods used in the maximum likelihood approach are not quite the same as the approximation methods used with the Mantel-Hansel approach. They're not exactly the same. So the confidence intervals can be different, and the formulas behind these two things are not quite the same. Okay. This brings up a whole issue that will be discussed in a later session, and that is, should we be using the approximations? Is it okay to use the approximating parabolas here? Is it okay to use the so-called asymptotic methods? Or should we be considering using so-called exact methods? It turns out exact methods for logistic regression are available and are becoming more and more widely used, but that's a whole other topic for now. For now, it is important for you to keep straight the fact that the models that we get from logistic regression may not give us the same fits, may not give us the same estimates as we get from stratified analysis. We hope those differences will be minor, but there's a fair bit in play here. Quite a bit of issue, I guess, eh? Okay. Some more terminology that you will be seeing right off the bat with the use of logistic regression. The first is maybe the most widely seen. It comes from the study of the likelihood function, and is the so-called likelihood ratio test. All statistical software does this. We will see that the likelihood ratio test is based on the comparison of two fits. The likelihood function is maximized with each fit, and then the maximum values are compared in a ratio, or the difference on the logarithmic scale. And the distribution theory, again, is an approximation based on the chi-square distribution. And the degrees of freedom of that chi-squared turns out to be the difference between the number of unknowns in the two fits, the two models. The likelihood ratio test is considered the definitive one when one is using approximate methods, for sure. Because we have, in fact, one more test that is also very widely seen and is displayed in standard output, as we will see in the illustrations to come. And that is also the so-called Wald test, named for Abraham Wald, also a major contributor to statistical methods. And in fact, it is just the ratio of the estimate to the standard error, and is based on an approximating standard normal value. Now, the Wald test turns out to be inferior to the likelihood ratio test in certain ways that we'll leave for the time being. But both the likelihood ratio test and the Wald test are approximate tests. It's just that it turns out that the likelihood ratio test has better so-called sampling properties. than the wall test has. Now, we would again expect that the p-values we get from the likelihood ratio test on the wall test should be fairly close. And if they're not, then again, the issue of should we be using an approximate method comes up. Okay, I think after that fairly intimidating and somewhat technical and maybe you're going to say somewhat theoretical first part to session 3, it's definitely time for some illustrations. We're going to take one particular data set and give it some intention. So we're going to have a circumstance in which we have an interest in a disease exposure relationship. And for our discussion for the moment, we're going to suppose that this can be interpreted as a cohort study or a prospective study. So what we're going to be interested in doing is studying the probability of disease. Okay? And exposure will be an explanatory variable. Okay. Let's first of all begin with just the crude. What do we see? Here's the example data. There's the 2x2 table. And with the CC command and stata, we get the estimate of the odds ratio. And you can check that that is in fact just AD over BC. Further, we get confidence limits for that. It is the estimate of the crude odds ratio, anticipating that there's going to be other characteristics that we wish to study. Just for interest's sake, we can see that although Stata reports a p-value with 0 and then 4 zeros, it is of value to note that that is just a very small number. It is not 0. And Stata gives you dutifully a number in exponential notation as 10 to the minus 13. You can ask this. So display, disp is for display here. Okay. How about now a stratified analysis? Let's stratify on smoking status. Okay, so we have a disease exposure relationship. And we have smoking status. What do we get? For the smokers, with S equals 1, we get an odds ratio estimate of just a little over 1. This is the same data, but now stratified by smoking status. Now let's look at the group with SM with smoking equals 2. Oh, we're right. Coding, right. The coding here is 1 and 2. So 2 is the non-smokers and 1 is the smokers, and we'll be coming back to this. Okay. I believe I've got that right. Anyhow. And what do we get? We get another point estimate that's just a hair bigger than 1. So in both the smokers and the non-smokers, what do we see? No evidence of a disease exposure relationship, whatever that is. So stratification appears to suggest that there is no disease exposure relationship. Remember the crude, though, we got a number of 3.5, a lower limit for the confidence interval, way bigger than 1, a p-value that is very small, whereas in both cases here, the p-values are way over 5%. Aha, now you're thinking, I know what this is. We did this. Here's the stratified analysis, essentially compactly combined. The two stratum-specific odds ratio estimates for the smokers and the non-smokers, the crude and the combined. Okay. So what do we got? Let's have a look. The test of homogeneity here, the Mantel-Hansel test for homogeneity here, is the test of whether or not there's modification. Or another way to spin it is the odds ratio for the smokers equal to the odds ratio for the non-smokers? That's the null hypothesis that's being tested here. And what do we see? We get a p-value that's way over 5%. So we have no evidence that the odds ratio for the smokers is different from the odds ratio for the non-smokers. Okay. So then we can think about the Mantel-Hansel combined. We can combine them. This is essentially a weighted combination of these two numbers. And we can then view the adjusted estimate here, or the estimate of the assumed common odds ratio, and compare it with the crude. And here again, we would say there is now clear evidence of confounding. This number 1, just a hair over 1, is obviously way different from 3.5. Now, in epidemiology, it is rarely seen that one would attempt a test of significance here. Rather, what you will see is certain guides for when to say there's evidence of confounding or not. This is a big and somewhat mysterious and somewhat far from complete issue. Some people say, well, if there's an absolute difference of a certain amount or a relative difference of a certain amount. We'll leave that topic for the time being. Maybe you've heard of these numbers, sometimes 10%, 15%, blah, blah, blah. The point being here is that whatever number we take, there's evidence that the crude is different from the adjusted, and we have evidence of confounding. Now notice the assessment of confounding is only made available to us because we have ruled out smoking as a modifier. Okay? So the combining of the two becomes available to us because there's no modification. Yep. Okay. We also get a test of significance for the assumed common odds ratio, and we see then that in this investigation there is no evidence of a disease exposure relationship. Okay. Or another way to spin it, again in the language that is often best to remind yourself of, there's no evidence against the hypothesis that there is no disease exposure association. Sounds like a double negative. Okay, so now let's see if we can take this on and consider the model-based version of this. So the first thing that I noted, just to be clear, is that the smoking characteristic was not an indicator. So the first thing we've got to do is construct an indicator variable. That's a variable that's just 0 or 1. So it'll be 0 for the non-smokers, and it'll be 1 for the smokers. Okay. Then we need that somewhat intimidating and rather mysterious term, which is the product of the disease indicator, DIS, and the smoking indicator. Again, that product may seem a little bit intimidating or mysterious, but its value is in what we get from the model that's fit, the interpretation of the regression coefficients we get from a model that includes that product of D times S. And indeed, if we fit such a model, the command in Stata is just logit. Then you specify the outcome, which is the exposure and the disease status. And we then have the smoking indicator and D times S. This is just like before. Okay. And what do we get? We get things that are very familiar with what we've seen before. Okay. What have we got? D times S. This is B3. This is the estimate of beta 3. And we can see that it's a small number. It has a large standard error. And the ratio of the estimate to the standard error, the Z is the wall test, has a p-value that's way over 5%. No evidence of modification. Okay. Stata will also enable you to construct the what we think are the odds ratios here. I'll come back to this. By adding the option OR, we get exactly the same fit, but now the numbers we get here are the exponents of the 4 regression coefficient estimates. Okay. Here's all the pieces. There's the model. In terms of the unknowns, the unknown conditional probability, the 4 unknown regression coefficients, and now we have the fitted values, and I've substituted them in here. So this table here can be written as now an equation in terms of the fit. And what do we see? We get some very familiar pieces here. Let's have a look. What is this number 1.15, which is the exponent of B1? Well, it turns out it's just the estimate of the odds ratio for the non-smokers. And there is the number right there. The 1.15 is the estimate of the odds ratio for the non-smokers. How about this number 0.873? Well, remember what that is. That's the estimate of the ratio of the 2 odds ratios. And you may want to go back to the appropriate slide where that's displayed. It is the ratio of the estimate of the odds ratio for the smokers divided by the odds ratio estimate for the non-smokers. It's noted, and it's maybe somewhat important here to notice, this number 0.8738 is not an odds ratio directly. It's a ratio of odds ratios. This can get more complicated in more elaborate situations, so we're going to have to come back to this. Okay, now let's look at a regression, a logistic regression without beta 3. So now we'll have exposure, disease, and smoking status. So that is what we called Model 2. Okay. No, it's Model 3. Right. So we've got Model 1, which is the crude, Model 2, which was the model with 4 terms, and Model 3, which is the model with 3 terms. Okay. Right. What do we got? We get now completely different numbers from what we got with the previous fit. And we can also get, by adding the OR option, the odds ratio estimates. And again, what I will refer you to, and you can go back to the technical part at the beginning of this session, but you will then be able to see that 1.07 is the maximum likelihood estimate of the assumed common odds ratio. As I mentioned earlier in this session, it is slightly different from the Mantel-Ansel estimate that we get from stratified analysis. Now, the confidence limits are almost the same as well, but not quite the same. Okay. So, in other words, we can then test a null hypothesis that the assumed common odds ratio is equal to 1. That we saw before was given to us by the Mantel-Hansel test in the logistic regression, in the stratified analysis. And we get a p-value of 0.770. There it is. Okay. Finally, we can think about the crude. Okay. And there it is, where we just have two regression coefficients, beta naught and beta 1. Oh yeah, and I don't know whether I've mentioned it explicitly, but when you see underscore cons like that for a constant term, okay, so this is the estimate of beta naught, and this is the estimate of beta 1. Okay, bit more. And there we have the familiar 3.5, which was the estimate that we got from the simple 2x2 table. It was just good old AD over BC. Yep. And it's the estimate of the crude. Okay. So what we can see is that for this example, the likelihood ratio test gives us almost the same p-value as the Wald test. I'll let you check this. So the LR test process here can be done. And we could compare the model 1 with model 2, and you can compare this information. However, we won't be interested in this. Our crucial interest is in the comparison of model 3 and model 2, which is giving us the likelihood ratio test for modification, which we've seen. Okay. Notice that we are getting quantities expressed in terms of the probability of exposure, the probability of exposure among the non-smoking controls, and so on. All of this can be done in terms of the log of the odds of exposure. Now, what we have next is a consideration of exactly the same thing, but where we're going to model the log of the odds of disease. So as I said at the beginning, which one do we want? Well, if it's a cohort study, we would probably want to model the log of the odds of disease. If it's a case control study, we would want to model the log of the odds of exposure. So this is a fairly large issue, and I'll be referring to some of the technical things here in a minute. But for now, let's suppose that we had not carried out the analysis in terms of the log of the odds of exposure, and had instead considered the analysis in terms of the log of the odds of disease. Well, it's pretty easy to do. Now we would construct the product of exposure times smoking status. So the indicator for exposure status multiplied by the indicator for smoking status, there it is. And now we got disease status as the outcome, exposure and smoking, and the product of exposure and smoking. Well. There's quite a bit going on here now. These two fits are not the same. The fitted values are not the same. On the other hand, there's one crucial thing here that is the same, and that is the estimate of beta 3 here is the same as the estimate of beta 3 we got in the previous fit. And the p-value based on the Wald test is the same. Oh my. This number is the same, it's the exponent of B3, and it is the same as what we got before. Well, well, well. Here are all of the pieces where I have redone the analysis in terms of the log of the odds of disease. And I would like to draw your attention then to the fact that some parts of this are the same and some are not. The best way to understand this is to interpret the coefficients and understand why things are the same and then why things are different. And so I'm giving you all of the pieces here, which you can study from the slides or from this video. So now I'd like to take a few minutes to discuss the issues that appeared right near the end of the illustration. And that was that we could model the log of the odds of disease, anticipating a study that is based on, say, a prospective analysis, a cohort study, or other variations on prospective studies. Or we could model the log of the odds of exposure if in fact the study was a case control study. Well, there's some very important issues here, and I don't propose to spend too much time on this here except to make some key points. And that is, if the model is being used for a case control study, then the most immediate analysis that's available to you is the model based on the log of the odds of exposure. However, for many years, investigators have wondered, what about modeling the log of the odds of disease? This is a complex issue, not straightforward. Recently has been very beautifully written and explained in a comparatively new book by Keogh and Cox. And the Cox there is Sir David Cox, who is the co-author of this amazing book, actually. Here's a little bit of the setup for this so that you can get a sense of the issues in play. Perhaps early in your course on statistics, you've seen some basic probability and the issues of marginal probabilities, conditional probabilities, and joint probabilities is discussed. Here's a little table then that shows the circumstances. We have got marginal probabilities in the margins, if you like, conditional probabilities available both ways, and the joint probabilities. Notice here that if it's all of the pieces here are available, we can discuss the probability of A given B, or we can discuss the probability of B given A. All are available. There's four of the joint probabilities, two of the marginal probabilities, probability A, probability of B, and again, these conditional probabilities. They're all available. And then we can compute the odds quite directly. We've got four odds. We've got an odds ratio. Notice this is the odds ratio where it's expressed into the odds of B in the presence of A divided by the odds of B in the absence of A. Call that odds ratio B. Odds ratio A is the odds of A in the presence of B divided by the odds of A in the absence of B. However, if the joint probabilities are available to us, those two odds ratios are the same. And there's a little bit of math that's needed. So if we think of now A and B as disease and exposure, if all of the probabilities up above here make sense, then the odds ratio D is equal to the odds ratio E. Or another way of spinning this is the odds ratio expressed in terms of disease. What do we mean here? That is the odds of disease for those exposed divided by the odds of disease for those unexposed. Whereas this number, ORE, is the odds of exposure for those with disease divided by the odds of exposure for those without disease. They're the same if, in fact, this makes sense. If we can think of the joint probabilities here. And a cross-sectional study might be an example in which we have all four. Okay? Now, what about a case control study? If we have a case control study, then we determine individuals with disease, the cases, and we determine individuals without disease, the controls. It's been noted that there is no probability distribution for case control status here. We can, though, speak of the conditional probability of exposure given disease, and similarly, the conditional probability of exposure given the absence of disease. Fair enough. Now, the challenge then is, this quantity, the odds ratio expressed in terms of exposure, is definitely available to us. What about the odds ratio in terms of disease? Well, in Keogh and Cox's 2014 book called Case Control Studies, they detail the three models that are at issue here. The population model they call the one that is based on the joint probabilities. That's where all of the pieces are available. The sampling model might be where we only have the probability of exposure for those with disease and the probability for exposure for those without disease. Okay, so that would be the real model, if I may, in a case control study. But then they then note there's a third model. They call it the inverse model, where one formally expresses the probability of disease for those exposed and the probability of disease for those not exposed. And they make it very clear in their book that this so-called inverse model is not giving us the distribution that generated the data. So this formulation in terms of the probability of disease is their so-called inverse model. So then they present the sampling model and the inverse probability model directly. And then they show that the maximum likelihood estimate from the sampling model is the same as the maximum likelihood estimate from the inverse model. These two numbers are the same. And the standard errors are the same, and the exact inferences based on the hypergeometric are the same. That's interesting, isn't it? Where we're modeling the probability of disease, and we're modeling the probability of exposure, but the crucial regression coefficient in this simple example are the same. But then they then point out that simple matter breaks down in more elaborate situations. Later in their book, they look at more elaborate models, of course. Then it can be pointed out that there's a wide class of models where the maximum likelihood estimates from the sampling model and the inverse model will be the same. But, unfortunately, there will also be many settings where the two models do not yield the same maximum likelihood estimates. But, as has been established through a fascinating literature and many important contributors to this literature, including Professor Ross Prentice, Canadian, who spent many years at the University of Washington. And it turns out that there's a theoretical justification for the inverse model. In other words, the theory of maximum likelihood is established all that many years ago by Sir Ronald Fisher, applies to the inverse models as well. Well, there's a lot at stake here. Many investigators would just say, "Oh, even if it's a case control study, you just model the log of the odds of disease, blah blah blah. Then you're done." It's not quite as straightforward as that. Many issues in play. The first one being that if the sampling model is not based on logistic regression, say in a circumstance in which exposure was, say, measured, it was on a continuum perhaps, then the sampling model might be based on linear regression and the study of expected exposure, and the inverse model would still be the logistic regression. And these two things are not the same. So the regression coefficients are not directly comparable in this instance. Okay. Also, the sampling model for the inverse model would give us very different diagnostics and fitted values. They give us different characteristics. So something else to keep in mind, that if you've made the decision to use the inverse model in your work, you have to keep in mind that the so-called sampling model would potentially give us very different interpretations and very different diagnostics and fitted values. Okay. I think that's all I'll say on this particular issue. You may have another illustration I've given here, but I'm just going to leave that for now. So I've got one more issue I want to briefly point out for you. And it brings up a point that some authors incorrectly interpret, and I thought it would be of some value just to make it clear here, or hopefully make it clear. So it turns out that some investigations are underway in which we wish to study the odds ratio, but other investigators might say, shouldn't we be using a rate ratio, like a risk ratio or a health ratio? Or shouldn't we be using a method, a model-based method, to analyze the rate difference? There's a lot of literature here that is still under exploration, actually. So logistic regression, very definitely the most widely used and, frankly, the most extensively researched. The models for the rate ratio and the rate difference are still comparatively new. And I'll be talking more about both of those in future sessions. Now, one of the comments that you will see when people are looking at a lot of data and they're looking at a lot of results from this data, maybe it's unclear from the way in which the report has been prepared as to whether or not they wish you to study the odds or interpret or consider the odds ratio, or do they wish you to consider the risk ratio? There's a whole swack of literature on this. There's even confusion over when the two are the same, and they're never exactly the same. That's another topic. But what you will often see is people drawing attention to the fact that in the results that are prepared, that the odds ratio is further from the null than the risk ratio in their data. And that somehow this makes it seem as though the odds ratio is better to use because it's further away from the null, right? Well, that has nothing to do with their data. In fact, one can show that the odds ratio is always further away from the null than the risk ratio. That it isn't just because of their data. Now, there's a fair bit in this, and I'm not going to go through it, the details here. There's just a couple of slides that you can review in your own circumstance. It turns out that both are relatively easy to show. Some simple math. And I've even come up with some displays that show the relationship between the two. Here's what it looks like. Isn't that something? That's almost artistic, I think, where I'm graphing the odds ratio versus the risk ratio. Fascinating. And the equality is along here. One more point that needs to be mentioned, and that is that the inequality showing that the odds ratio is always further from the null than the risk ratio is a little more elaborate than maybe you might be thinking, or maybe what I actually just said at the beginning of this section. So it turns out that the crude estimates and the stratum-specific estimates satisfy that inequality. The odds ratio will always be further from the null than the risk ratio. Well, it turns out that this is a little more complicated if we're using, say, a stratified analysis using Mantel-Hansel methods, or we're using maximum likelihood methods. Turns out that the adjusted odds ratio and the adjusted risk ratio may not directly satisfy this inequality. So I'm going to leave it at that, except to point out that this particular topic is still an active area of research. And with that, I will close session number 3.